Hi, everybody. This is Mr. Polly, and whoa, it's drawn like crazy. And welcome to me doing your homework with you. Shown below are different particle pictures. Determine what is wrong with the particle picture and explain how it should be fixed to be accurate. A gas contained in a rigid container. How would you fix the picture? I need to have some of these particles here, some of these particles here, some of these particles here, some of the particles in the middle, which to put that in English means spread out Mickey Mouses. Separate gases are allowed to mix. So right here, when they're mixing, after mixing, red is lighter. Oops. So if it's lighter, so what's going to happen is reds will be in here, reds will be in here, reds will be in here, and blues will be in here, and blues will be in here. And it doesn't really show it very well, but the reds would move faster than the blues. So separate gases are allowed to mix. It will end up being a homogeneous mixture of red and blue. That means every sample will be the same. A particle picture of Li2SO4. Okay, so this is Li, which would be positive, and this is SO4, which as a group would be -2. So when I have Li2SO4, I need to have another Li. So I need to have another one of these. And the other one should be a particle picture, should be many of them. So this doesn't look the way I want it to. It should be a lattice of 2 browns for each SO4. And this is my SO4. Okay. A particle picture of iron 2 sulfate. Now, iron 2 sulfate, remember it's iron 2 sulfate, that means it's going to be Fe plus 2, SO4 -2. So again, it should be a lattice, which means it should be a repeating pattern of it, but there should be 1 positive for 1 negative ion. And again, the negative ion, well, this would be the sulfate. So this one should go away. Okay. Particle picture of a chemical reaction. Uh-oh, it added an X for me. So if these react, I need to have it needs a new product. Well, I put a new products. Good job with the verb tense. Needs a new product. So it might be a big and a little. Okay. You could have a big, little, right? But it needs to have a new product with bonds. In this case, it would have to have bonds because the other ones didn't. Particle picture of a physical change. Physical change, triangle means change, means, NS, no new products. So that just means mix only. So that would mean I'd have a red one, and then I'd have a green one. Oops, my circles aren't doing so hot. So I'd have a red, and I have a green mixed together, and a red and a green and a red and a green and a red and a green. So see these guys? I would have C and D. So if I were to redraw this, I'd have C, D, C, D, C, D, C, C, D, D. Okay. It doesn't have to be a homogeneous mixture, but it does have to be a mixture. Use the key below to draw the solutions indicated. Any positive ions, any negative ions, and we're not doing water. So any positive ion KCl would be filled in, circle, circle, filled in. So that's dilute, so there's not a whole lot of them. I'm going to actually make it look a little more mixed. Okay. Concentrated KCl. So this one in the same box, I had 3. So I'm going to put 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 6. So I just have more of them in there. dilute AlNO3. So Al is the dot, so I'm doing my dots with 1, 2, and then because I have 3 of these, right, I need to have 6 negative ions. 1, 2, 3, 4, 5, 6. Uh-oh, these 2 touched. So it got all kinds of crazy. All right, concentrated. So I had 2 dots before, so I'm going to do 4 dots. 1, 2, 3, 4, which means I need 4 times 3, 12 circles. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. And again, I need to make sure I know the computer is making these go weird on me, but they shouldn't be touching. Good. So remember, concentrated just means you have more of it. Okay, it doesn't have to be exactly double, but that's it. And A3PO4 is going to have 1 dilute, 2, 3, 4, 5, 6. So what I'm looking for here is I'm going to put 2 of these. If I have 2 of those, I need 6 of those. So I need to put just 2 big circles now. Good. Student mixes 100 milliliters of Na2CO3 with an excess amount of calcium nitrate. The equation shown below. Okay, 100 milliliters, but it doesn't give me a molarity. With an excess of that, I get a precipitate. The diagram showing the beaker where the reaction takes place is incomplete. Draw the species needed to accurately represent the major ionic species remaining. So an excess. So I have excess to this. Well, it won't let me draw my excess. That's interesting. So I guess that means we are done. Oh, here it goes. It came back. So it won't let me draw that this is excess. It should. So that means that for calcium carbonate, that's my precipitate. So what that means is I should have excess Ca, and I should have no extra CO3, right? Because this is limited, right? The NAs will still be there though, okay? So there's solid CaCO3. So a diagram showing the beaker reaction takes place is incomplete. Draw the species needed to accurately represent the major ionic species remaining. So no extra CO3 -2, but yes, Na positive. Oh man. So I should have extra calcium, right? So calcium's in excess, so I need to have a calcium +2 in there. And then nitrates, I used some of them, so if I got 1, 2, 3, 4, that'll work. And then, yep, that's it. All missing is calcium +2. You could put in more if you wanted to, but you can't really tell. Beaker X contains solution AgNO3, while beaker Y contains a solution MgCl2. Answer the questions that follow about the reaction that occurs between these two. So this is my precipitate, which is what we care about. Okay. Determine which beaker below is correct for beaker X. So X should have 1 part sodium and 1 part nitrogen, so they should equal each other out. Explain your reasoning. So it should be equal Ag equals NO3. Okay, so 1, 1, little, 2, little, 3, little, 4, 5. And this should be the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's not that one. Silver, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, nitrates, 1, 2, 3, 4, 5, 6, 7, 8, 9. Seriously? 10. There it is. Okay, so this is the right one. Why? Ag positive equals NO3 negative. Determine which beaker below is correct for beaker Y. Beaker Y should have 2 Cl negatives for 1 Mg plus 2. Okay, there's my explanation. So again, notice how I don't look at the choices. I look at what the answer should be and I go find it. So I should have 2 negatives. So I have 1, 2, 3, 4, 5. That's not going to be it because you can't have 5 negatives. I got to have an even number. So 1, 2, 3, 4, 5. This is really annoying because that shouldn't be that way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 1, 2, 3, 4, 5. So notice you can't have an uneven number when you're doing particle diagrams like that. Oh, look at this already, page 4. In letters A through C below, amounts of chemical reaction are given. Use the key below to draw the reactants in beaker X, the reactants in beaker Y, and the products in beaker Z. In each case, calculate the mass of AgCl formed in the reaction. Okay, so I've got 0.01 mole of Ag. Do I have that balanced reaction here? I do not. Oh, here it is. So I got to write the reaction myself. So we do know that the precipitate is AgCl, so that's all that we care about. I got caught in that thing. Okay, so all we care about is AgCl. So I'm going to look for Ag positive plus Cl negative yields AgCl. And that's what I'm looking for. Okay, I don't care about the rest of the stuff. So if I have 50 milliliters of 1 molar AgNO3, so it's helpful to know that moles equals M of V. That's just rearranging the molarity problem. So 1 times 0.05 is 0.05 moles of that. And over here, it's the same thing. So I have 0.05 moles of that. Okay. So in this case, I have extra Cl negative. So that means in beakers Z, I know I'm going to have some Cl negative left over, right? And I know that I'm going to have some Mg plus 2 left over. I'm going to put 2 of those because I don't have extra of that. And I'm going to have nitrate left over. I'm going to put 2 nitrates. So over here, I'm going to have, so I'm going to start with equal amounts of this, beaker X. So I'll put Ag positive, I should spread them out more because they should be homogeneous mixtures, but Ag positive, NO3 negative, NO3 negative, Ag positive. And then beaker Y, same thing, Mg plus 2, Mg plus 2, but I'm going to have double chlorines because it's got a 2 here. Okay, and then all my Ags are used up, but I got one of these left over. Those didn't react, and those didn't react, so I'm good. All right. Okay, so this is a little different. So 0.01 mole, so all I care about is this guy and this guy because this is my precipitate. Because remember, I'm just looking for Ag positive plus Cl negative yields AgCl. Okay, so if I have that, I have one. Oh, this isn't quite the same, is it? Oh, they're giving me molarities for that? I'm just going to keep rolling with what I got. So remember, mole equals MV. So that's going to be 1 times 0.1, which is going to be 0.1. Oops, 0.1 moles of AgNO3. And the same thing is going to be true. Oh, no, it's not. Here I'm going to have 0.05 moles of MgCl2. So it's going to be half as much. Okay. So that means for AgNO3, I suppose I'll put 2 of them in there because that'll make my math a little easier. Ag positive, NO3 negative, NO3 negative, and this one's going to be half as much, right? So it's half as much. I'll have 1 Mg plus 2, and that's it, right? And then I have to double my chlorides, right? So I get AgCl, so I have 2 Ags and 2 Cls, and that'll take care of those. And all I have left floating around is Mg plus 2 because it wasn't used, and the 2 nitrates which weren't used, NO3 negative, NO3 negative. All right, here we go again. 150 milliliters, so moles equals MV, so this is going to be 0.15 moles, and this is going to be 0.05 moles. So notice I got a 3-to-1 deal going on here now. So that means I'll go ahead and put 3 Ag positives on here. And I have to put 3 nitrates. And I'm doing this because this is a 3-to-1 ratio. Oh, that's not what I'm doing it for that. Yeah, 3-to-1 ratio. So then when I do this, I'll have 1 Mg plus 2. So that's 3 Ag positives to 1 Mg plus 2. Okay. And then if I have one of those, I'll still have 2 chlorides. And I do wish these were balanced more, but yeah, I'm okay with it. AgCl is going to react as much as it can. So 1, 2, 1, 2. You see I have an Ag positive left over. And then I have an Mg plus 2 left over. And I have 3 nitrates. I think about it, they give us these pictures, and I guess I could have drawn those. What happened to me? So put this guy back up there. Good. I suppose I could draw it like that, but I'm not gonna. Use the beakers draw an accurate representation of CuNO3. Okay, so notice Cu equals NO3. So if I've got 1, 2, 3, 4, 5, 6, 7, 8, I need to have 8. 1. I'm just going to make those shady. 1, 2, 3, 4, 5, 6, 7. Did you enjoy me counting? I enjoy counting. It's very relaxing. CuNO3 taken twice, so that means I have 1 copper for every 2 nitrates. 1, 2, 3, 4, 5, 6, 7, 8. So I need 4 of these guys. 1, 2, 3, 4. I don't know why they're running, but they are. In the box below, draw the most likely orientation of 4 water molecules. So remember, this is the negative end, and these are the positive ends. Okay? So 4 of them. 1, 2, 3, 4. Because the negative is attracted to the plus 2. Hey, there's a water floating around. Shown below is a representation of water in a crystal of liquor. Answer the question to follow, making a solution of liquor. Okay, so remember, positive is small, and the chloride is bigger. And if you look, it's on the second energy level. Oh, I'm sorry. Li plus 1 is on the first energy level because lithium's on the second, and that's it. And chlorine is on the third energy level, so it's going to be a lot bigger. Okay. So remember, the first positive one is smaller, negative one is bigger. So I got to draw some water. 1, 2, 3, 4, 5, 6. Okay. And it says, oops. So I'm going to draw that, and then I'm going to do, that's the negative one. So 1, 2, 1, 2, 1, 2. That's good enough. Okay. Determine the identity of each particle below. Explain your reasoning. I did that. First energy level for Li positive. It lost a level from 2. This is on the third energy level because that's where chlorine is. Cl negative gained and filled. Third. Okay. Space provided below. Show the interactions of the components of LiCl by making a drawing that represents different particles present in solution. Base the particles in your drawing on the particles shown in the representation above. Include only 1 formula unit of LiCl and no more than 10 molecules of water. Your drawing must include the following details and identify ions. So this is the little one, and it's going to be plus, and then we'll have a big one, and it'll be minus. Okay. The arrangement and proper orientation of particles in solution. So I'm going to have, how many of these are supposed to have? Include only 1 formula unit, so a circle and a square. Okay. And since this is my positive one, I guess I'll put my little positive in there. No more than 10. 1, 2, 3. So remember, the negative chin of water is close to the positive one. And then the positive ears are attracted to the, and it doesn't have to be perfect left, right, whatever it is, but that way it's 8, and that's good. All right, briefly describe the separation technique and explain when the technique should be used. Filtration, describe it. Pour a mixture of solid and solution through a filter and solid is caught in filter. And when to use it? When you have a solid and a solution. Paper chromatography, briefly describe each technique. And a dye or an ink flows with a solvent at different rates. I'm going to put dyes flow with the solvent at different rates to identify or separate dyes, typically with inks. Column chromatography. Briefly describe it. Flush a liquid mixture through a polar-filled gooey. Whoops, I put F for gooey. Come on. Gooey pipette. Burette probably. But it won't. There you go. Burette. Separate mixtures of different polarities. Mixtures of solutions of differing polarities. I'm supposed to put my ass back up there. Distillation. What happens? Heat a mixture and collect. I'm going to say recollect liquids after they boil. I'm going to use it to separate liquid mixtures. And I could say with different boiling points, but almost everything has a different boiling point. So that's good. That's 22 minutes of fun, and that got us to page 7. So that got us halfway there. I kind of like that. So to that, I will say toodles.